Tonight we're going to explore something that sounds simple, but reveals just how trapped we really are. We're going to answer one straightforward question. How long would it actually take us to travel 1 light year? Not in theory, not with imaginary technology, with what we have right now. And by the end of tonight, you're going to understand why the stars might as well be painted on the ceiling of a cage we can never escape. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what a light year actually is, because most people misunderstand this from the beginning. A light year isn't a measure of time, it's a measure of distance. It's the distance light travels in 1 year. And light moves fast, unimaginably fast. Light travels at about 186,000 meters per second. In 1 second, light could circle Earth's equator about 7.5 times. In 1 second, light travels farther than most people will travel in their entire lives. Let that sink in for a moment. In the time it takes you to blink, light has already crossed a distance equivalent to 3 trips around the entire planet. Now multiply that speed by the number of seconds in a year. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. That gives us about 31,536,000 seconds in 1 year. Light travelling at 186,000 meters per second for 31,558,000 seconds covers a distance of about 5,870,000,000 miles. And here's the critical question we're exploring tonight. How long would it take us to travel that distance? Let's start with the fastest thing humanity has ever built, the Parker Solar Probe. Launched in 2018, the Parker Solar Probe is a NASA spacecraft designed to study the Sun. It's designed to dive closer to the Sun than any spacecraft in history, passing through the Sun's outer atmosphere, the corona. To collect data about solar wind and the Sun's magnetic field to do this without melting, it has to move incredibly fast. At its maximum speed, the Parker Solar Probe reaches about 430,000 miles per hour. That's the fastest any human-made object has ever travelled, about 119 meters per second. For comparison, a bullet from a high-powered rifle travels at about 1 meter per second. The Parker Solar Probe is moving 119 times faster than a speeding bullet, and it's still pathetically slow compared to light. Light travels about 1,560 times faster than our fastest spacecraft. So how long would it take the Parker Solar Probe to travel 1 light year? 1 light year is about 5,870,000,000 miles. At 430,000 miles per hour, that works out to about 1,560 years. Let me put that in perspective. That's about the time from the fall of the Roman Empire in the year 476 to today. It's roughly the entire span of the Middle Ages and the modern era combined to reach Proxima Centauri. The nearest star at 4 1/4 light years away would take over 6,600 years. By the time it arrived, humanity would either be extinct, evolved into something unrecognizable, or spread across the galaxy with technology that makes the Parker Solar Probe look like a wooden cart. Or maybe we'd still be here on Earth, having forgotten we ever launched it. Now you might be thinking, well, the Parker Solar Probe wasn't designed to travel to other stars. It was designed to study the Sun. What if we built something specifically designed for interstellar travel? What if we used our best rocket technology and optimized everything for speed? Let's look at the Voyager probes. Voyager 1 and Voyager 2 were launched in 1977. They're both still operational, still sending data back to Earth after more than 45 years in space. Voyager 1 is currently the most distant human-made object from Earth. It's about 14-12 billion miles away, well beyond the orbit of Pluto, travelling through interstellar space. Voyager 1 is moving at about 38,000 miles per hour relative to the Sun. Much slower than the Parker Solar Probe, but still incredibly fast by everyday standards. At that speed, Voyager 1 could travel from Los Angeles to New York in about 4.5 minutes. But how long would it take Voyager 1 to travel 1 light year? At 38,000 miles per hour, that works out to about 17,600 years. That's more than 11 times longer than the Parker Solar Probe. The Voyager probes are amazing achievements. They've lasted longer than anyone expected. They've sent back images and data from Jupiter, Saturn, Uranus, Neptune, and now from interstellar space itself. But they're slow. Let's try something different. What if we used nuclear propulsion? Nuclear rockets have been studied extensively. The basic idea is to use a nuclear reactor to heat propellant to extremely high temperatures and expel it out the back of the spacecraft. This can theoretically achieve much higher speeds than chemical rockets. In the 1950s and 60s, there was a project called Project Orion. The idea was radical. Instead of using a nuclear reactor, you detonate nuclear bombs behind the spacecraft. Each explosion would push against a massive shock absorber plate, propelling the spacecraft forward. It sounds insane, and in many ways it is, but the physics actually works. Calculations suggested that an Orion-style spacecraft could potentially reach speeds of about 3 to 5% the speed of light. Let's be optimistic and say 5%. At 5% the speed of light, it would take 20 years to travel 1 light year. That's actually conceivable. That's within a human lifetime. If you left Earth at age 25, you'd arrive at your destination at age 45, still young enough to explore, still young enough to contribute to a new colony, still young enough to see the results of your journey. But here's the problem. Project Orion was never built. It was studied extensively. Engineers worked out the details. They calculated the size of the bombs, the mass of the shock absorber, the trajectory through space. They figured out how to protect the crew from radiation. They designed life support systems, but it was never built, and it probably never will be, at least not with nuclear bombs. The main problem is political and practical. Launching nuclear weapons into space is banned by international treaty. The Partial Test Ban Treaty of 1963 and the Outer Space Treaty of 1967 both prohibit nuclear weapons in space. Even if those treaties didn't exist, the technical challenges are enormous. You would need to carry thousands of nuclear bombs with you. Each one would need to be perfectly timed and positioned. A malfunction could destroy the spacecraft. The radiation exposure for the crew would be significant, even with shielding, and the cost would be astronomical. So, Project Orion remains a fascinating idea, a theoretical possibility, but not something we're actually going to build anytime soon. What about other forms of nuclear propulsion? There's something called nuclear electric propulsion. This uses a nuclear reactor to generate electricity, which then powers an ion drive or similar electric thruster. Ion drives work by accelerating ions-charged particles to very high speeds and expelling them out the back of the spacecraft. The thrust is tiny, but it's continuous, and over time you can build up impressive speeds. NASA's Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, used ion propulsion. It was powered by solar panels, not a nuclear reactor, but the principle is the same. Dawn achieved a total change in velocity of about 25,000 miles per hour over the course of its mission. That's impressive for its size and power to budget, but it's still far too slow for interstellar travel. Even with a much larger nuclear reactor providing more power, nuclear electric propulsion would probably only achieve speeds of about 1 to 2% the speed of light at best. At 1% the speed of light, it would take 100 years to travel 1 light year. That's longer than a human lifetime. You'd need multiple generations. A crew would leave Earth knowing their grandchildren would be the ones to arrive at the destination. This is the concept of a generation ship, and it brings up all sorts of challenges. How do you maintain a closed ecosystem for 100 red years? How do you prevent the ship from breaking down? How do you maintain social cohesion when everyone knows they'll die before reaching the destination? How do you prevent genetic problems from inbreeding in a small population? These aren't impossible problems, but they're difficult, and we haven't solved them yet. So nuclear electric propulsion might get us to 1% the speed of light, maybe 2% if we're optimistic. That's still 50 to 100 years to travel 1 light year. What about fusion? Nuclear fusion is the process that powers the sun. It involves forcing hydrogen nuclei together under extreme temperature and pressure until they fuse into helium, releasing enormous amounts of energy. We've been trying to build practical fusion reactors on Earth for decades. We've achieved fusion in laboratories. We've even achieved net energy gain where the fusion reaction produces more energy than it took to start it. But we still don't have a working fusion power plant. The engineering challenges are immense. You have to contain plasma at temperatures of millions of degrees. You have to maintain that containment long enough for the fusion reactions to produce useful energy. You have to extract that energy efficiently. It's difficult, and we're still working on it. But let's assume we solve it. Could we use fusion for spacecraft propulsion? Theoretically, yes. A fusion rocket would heat propellant to incredible temperatures using fusion reactions and expel it at extremely high speeds. If you could continuously accelerate at a reasonable rate using fusion propulsion, you might be able to reach 10 to 20% the speed of light. At 10 to 20%, you're looking at 5 to 10 years to travel 1 light year. This is starting to look almost practical. 5 years is a long time, but it's within the range of what humans have already done. Astronauts have spent over a year in space on single missions. 5 years would be challenging, but not impossible. But here's the reality. We don't have fusion propulsion. We don't even have fusion power plants on Earth yet. Building a fusion rocket capable of accelerating to 10 or 20% the speed of light would require solving all the problems of fusion power, plus additional problems of miniaturization, shielding, propellant storage, and spacecraft design. It's probably decades away at minimum, possibly centuries. So fusion propulsion is theoretically possible, but practically we're nowhere close. Now let's talk about the most speculative ideas. What if we could somehow travel at a significant fraction of the speed of light? Not 5 or 10 or 20%, but 50%, or even 90%. There have been various proposals. Antimatter propulsion is one. When matter and antimatter come into contact, they annihilate each other completely, converting all their mass into energy. According to Einstein's famous equation, E equals mc squared, this is the most efficient energy conversion process we know of. A kilogram of antimatter annihilating with a kilogram of matter would release about 180 times more energy than a kilogram of hydrogen undergoing fusion. If you could harness this energy for propulsion, you could theoretically achieve very high speeds. Some estimates suggest antimatter rockets could reach up to 70 or 80% the speed of light. At those speeds, you'd travel 1 light year in about 15 to 17 months. This is genuinely fast. You could reach Proxima Centauri in about 5 or 6 years. You could reach stars dozens of light years away within a human lifetime. But there's a problem, actually several problems. First, we can't produce antimatter in meaningful quantities. Antimatter can be created in particle accelerators, but only in tiny amounts. CERN's particle accelerators produce about 1/billionth of a gram of antimatter per year. At that rate, it would take about 100 billion years to produce 1 gram. That's longer than the current age of the universe. Second, storing antimatter is incredibly difficult. Antimatter annihilates on contact with normal matter, so you can't just put it in a container. You have to trap it using magnetic fields, suspending it in a perfect vacuum. We can do this for individual particles or small clusters, but scaling it up to the kilograms or tons you'd need for a spacecraft is far beyond current technology. Third, the energy released from matter-antimatter. Annihilation would be difficult to harness efficiently. A lot of it would come out as gamma rays and neutrinos, which are hard to capture and direct for propulsion. You might only be able to use a fraction of the energy effectively. Fourth, even if you solved all these problems, the spacecraft would need enormous shielding to protect the crew from radiation. At high fractions of the speed of light, even tiny dust particles in space become dangerous. A grain of sand hitting your spacecraft at 80% the speed of light would release energy equivalent to a large bomb. You'd need meters of shielding, which adds mass, which requires more fuel, which adds more mass. It's a vicious cycle. So antimatter propulsion is theoretically possible, but practically it's science fiction. We're not close to building it, and we might never be. What about concepts that don't require carrying your own fuel? There's an idea called a laser sail or light sail. The basic concept is simple. You build a spacecraft with a large, thin, reflective sail. You shine a powerful laser from Earth onto the sail. The photons from the laser bounce off the sail and transfer momentum, pushing the spacecraft forward. Because you're not carrying fuel, your spacecraft can be very light, which means even a small amount of momentum transfer can produce significant acceleration. There's a project called Breakthrough Starshot that's exploring this idea. The plan is to build thousands of tiny spacecraft, each weighing only a gram or two, equipped with light sails a few meters across. Ground-based lasers would accelerate these tiny probes to about 20% the speed of light. At 20% the speed of light. They'd reach Proxima Centauri in about 20 years. They'd fly past taking pictures and measurements and beam the data back to Earth. The data transmission would take another 4 years to reach us. So the total mission from launch to receiving data would be about 24 years. This is genuinely exciting. It's theoretically possible with technology that's not too far beyond what we have now, but there are significant challenges. The lasers would need to be incredibly powerful, combining the output of many individual lasers to create a beam strong enough to accelerate the probes. The aiming would need to be perfect, the sails would need to be incredibly lightweight and reflective. The spacecraft would need to survive the intense laser heating during the acceleration. And perhaps most significantly, the spacecraft would be tiny. A 1G spacecraft can't carry much in the way of instruments or power supplies. It would basically be a camera, a transmitter, and not much else. It couldn't slow down when it reached its destination. It would just fly past at 20% the speed of light, taking pictures for a few minutes at most, then continuing into the darkness. Still, Breakthrough Starshot represents one of the most realistic proposals for interstellar travel we have. It's actually being worked on. Engineers are building prototypes. They're testing materials. They're calculating trajectories. It might actually happen within the next few decades. But even with laser sails, reaching 20% the speed of light, traveling 1 light year would still take 5 years. And that's assuming everything works perfectly. So let's step back and look at what we've learned. With our current fastest spacecraft, the Parker Solar Probe traveling 1 light year would take about 1,560 years. With the Voyager probes, it would take about 17,600 years. With theoretical nuclear pulse propulsion like Project Orion, it might take about 20 years, but we're not building it. With nuclear electric propulsion, it would take 50 to 100 years, and we don't have that technology yet. With fusion propulsion, it might take 5 to 10 years, but fusion reactors don't exist yet. With antimatter propulsion, it might take 1 to 2 years, but antimatter production and storage are far beyond our capabilities. With laser sails, it might take 5 years for a tiny probe weighing a gram, but even that technology is still experimental. The reality is sobering. We cannot travel to the stars with current technology. We can barely leave our own solar system. Voyager 1, after 45 years of travel, is only 2 light years from Earth. It's travelled 2/10,000ths of a light year. To travel 1 full light year at Voyager's speed would take 17,600 years. The stars are so far away that even light, the fastest thing in the universe, takes years to travel between them. And we are so slow compared to light that the journey becomes almost meaningless. 1 light year might as well be infinity. We can't cross it in any practical sense, not in a human lifetime, not in many human lifetimes. The astronomer Carl Sagan once said that the cosmos is all that is or ever was or ever will be. But for us, for humanity as we exist now, the cosmos might as well be just our solar system. The stars beyond are beautiful to look at. They're fascinating to study, but they're not places we can go. They're not destinations. They're just lights in the sky, forever out of reach. This is the harsh reality of the universe we live in. The distances between stars are so vast that they're effectively impossible with anything remotely resembling current technology. Even with optimistic projections of future technology, travelling 1 light year would take years at minimum, possibly decades or centuries. Now, this doesn't mean interstellar travel is impossible forever. Technology advances. We've gone from the Wright brothers' first flight in 1903 to landing on the moon in 1969. That's only 66 years from the first powered airplane to humans walking on another world. Maybe in another century or two we'll have fusion drives or antimatter engines or something we haven't even imagined yet. Maybe we'll figure out how to build generation ships that can sustain human populations for thousands of years. Maybe we'll develop artificial intelligence that doesn't need life support and can travel for millions of years without concern. Maybe we'll discover new physics that allows faster than light travel, though that seems extremely unlikely given our current understanding. But with what we have now, with what we'll have in the foreseeable future, the stars remain out of reach. 1 light year is an impossible distance, and the nearest star is more than 4 light years away. Let me give you one more perspective to drive this home. The fastest speed any human has ever travelled was during the Apollo 10 mission in 1969. The command module reached about 24,791 miles per hour during re-entry. That's about 6.89 meters per second. At that speed, travelling 1 light year would take about 27,000 years. The astronauts on Apollo 10 travelled faster than any humans before or since, and they'd still need 27,000 years to cover 1 light year. 27,000 years ago, the ancestors of modern humans hadn't evolved yet. We were still small primates living in trees. The entire evolution from those small primates to modern humans would need to happen with all the glacial ages, all the evolutionary adaptations, all the slow changes, and you still wouldn't have arrived yet. This is the scale we're dealing with. This is why 1 light year might as well be infinite. Some people find this depressing. The idea that we're confined to our solar system, that the stars are forever beyond our reach, that the universe is so vast and we're so slow. But there's another way to look at it. Our solar system is actually pretty big. Earth is tiny, yes, but the solar system extends far beyond the planets. The Kuiper belt, where Pluto orbits, is about 4 billion miles from the Sun. Beyond that is the scattered disk extending out to about 9 billion miles. Beyond that is the Oort cloud, a spherical shell of icy objects that extends out to about 1 light-year from the Sun, maybe even 2 light-years. The Oort cloud is still gravitationally bound to the Sun, still part of our solar system. So our solar system might actually be about 2 light-years across. That's a lot of space. There could be millions or billions of objects in the Oort cloud. We've barely begun to explore the outer solar system. We've sent probes to the planets. Yes, we've studied Jupiter and Saturn and their moons. We've flown past Pluto, but the vast majority of the solar system remains unexplored. There could be undiscovered dwarf planets out there. There could be unusual objects with strange orbits. There could be resources we haven't imagined. Maybe instead of trying to reach other stars, we should focus on thoroughly exploring and utilizing our own solar system. Maybe there's enough here to keep humanity busy for thousands of years. We could build habitats on asteroids. We could mine the moons of Jupiter and Saturn for water and minerals. We could establish research stations throughout the outer solar system. We could study the Oort cloud and the Kuiper belt. We could create a civilization that spans the solar system with billions of people living in space habitats on terraformed moons, on artificial worlds. And maybe centuries from now, when we've fully developed our solar system, when we've advanced our technology far enough, we'll be ready to take the next step. We'll build generation ships powered by fusion or antimatter. We'll send them to nearby stars, knowing the journey will take decades or centuries, and humanity will slowly, patiently spread to other stars, one system at a time, over thousands or millions of years. But that's a long way off. For now, for our lifetimes, for our children's lifetimes, probably for our grandchildren's lifetimes, we're confined to this solar system. And when you ask how long it would take to travel 1 light-year, the honest answer is too long. Far too long for any practical purpose with current technology. Too long for a human lifetime. Too long for many human lifetimes. The universe is vast and we are slow. The stars are distant and 1 light-year might as well be forever. But we're here. We're on Earth, orbiting our sun in our solar system. And maybe that's enough. Maybe for now, home is enough. Let me leave you with one final thought. The speed of light is often called the cosmic speed limit. Nothing can travel faster than light according to our current understanding of physics, and light takes 1 year to travel 1 light-year by definition. If we could somehow travel at the speed of light, which we can't because anything with mass would require infinite energy to reach light speed. But if we could, travelling 1 light-year would take 1 year. But here's something strange. From the perspective of the traveller, time dilation effects mean that the journey would seem shorter. At 99% the speed of light, time slows down significantly. A journey that takes 10 years from Earth's perspective might only feel like 1.4 years to the traveller. At 99.9% the speed of light, a 10-year journey would feel like only about 5 months. At 99.99% the speed of light, it would feel like about 2 weeks. And at exactly the speed of light, if it were possible, no time would pass at all from the traveller's perspective. From a photon's point of view, the journey from one side of the universe to the other is instantaneous. Of course, we can't reach the speed of light. We probably can't even reach 99% of it. The energy requirements are absurd and the engineering challenges are insurmountable with anything we can imagine building. But it's interesting to think about. The universe puts fundamental limits on how fast we can travel. Those limits make the stars unreachable with current technology. They might make the stars unreachable forever. Or they might just mean we need to be patient to develop our technology slowly over centuries or millennia until we're ready. Either way, the answer to how long it would take to travel 1 light-year is clear. With what we have now, it would take over 1,000 years. With optimistic future technology, it might take decades or centuries. With technology that might never exist, it could take years or months, but the stars remain distant. 1 light-year remains an almost infinite distance. And for now, we remain here on this small blue world, looking up at lights we can see but cannot touch. The universe is beautiful, the stars are magnificent, but they're far away, so far away that 1 light-year might as well be the edge of reality itself. Thanks for staying with me through this journey. The question was simple, but the answer reveals something profound about our place in the cosmos. We're bound to our solar system by the vast distances of space and the limitations of physics. The stars are there, we can see them, we can study them, but we can't reach them, not yet, maybe not ever. And in that limitation, there's both humility and wonder. Humility because we're reminded how small and slow we are. Wonder because the universe is so vast, so full of places we can imagine but never visit. At least not in our lifetimes. 1 light year, a simple unit of distance. But crossing it would take longer than human civilization has existed. And that's the reality we live with. That's the cage of distance and time that binds us to this corner of space, and maybe that's okay. Maybe being here on Earth in this solar system is enough, because home isn't measured in light years. Home is measured in moments in the people and places that matter to us. And our home, this solar system, this Earth, is right here, not 1 light year away, not 1,000,000 years of travel away, right here. And sometimes right here is exactly where we need to be. But let's dig deeper into why this distance is so impossible. Let's talk about the physics that makes 1 light year such an insurmountable barrier. It's not just about building a faster engine, it's about fundamental limitations built into the fabric of reality itself. When we talk about traveling close to the speed of light, we're not just talking about engineering challenges. We're talking about energy requirements that boggle the mind. Einstein's theory of special relativity tells us that as you approach the speed of light, your mass effectively increases. The closer you get to light speed, the more energy it takes to accelerate further. At 90% the speed of light, your effective mass is about 2.3 times your rest mass. At 99%, it's about 7 times your rest mass. At 99.9%, it's about 22 times your rest mass. And at exactly the speed of light, your effective mass becomes infinite. This means the energy required to accelerate you to light speed also becomes infinite. It's not just a practical impossibility, it's a fundamental impossibility according to the laws of physics as we understand them. You cannot reach the speed of light if you have mass. Only massless particles like photons can travel at light speed, and they always travel at light speed. They can't go slower, they can't go faster. They just travel at light speed from the moment they're created until the moment they're absorbed. So if we can't reach light speed, what's the maximum speed we could theoretically achieve? Let's think about energy. The kinetic energy of an object in classical physics is 1/2 times mass times velocity squared. Double the speed and you need 4 times the energy. Triple the speed and you need 9 times the energy. But this formula breaks down as you approach the speed of light. At relativistic speeds, the energy requirements grow much faster. To accelerate 1 kilogram to 10%, the speed of light requires about 4.5 times 10 to the 14th joules. That's about the energy in 10,000 kilograms of gasoline. To accelerate 1 kilogram to 50%, the speed of light requires about 1.3 times 10 to the 16th joules. That's about the energy in 300,000 kilograms of gasoline. To accelerate 1 kilogram to 90%, the speed of light requires about 1.2 times 10 to the 17th joules. That's about the energy in 2.8 million kilograms of gasoline. Notice how the energy requirements are growing faster than the speed. Going from 10% to 50% light speed, you multiply the speed by 5, but the energy goes up by about 29 times. Going from 50% to 90%, you multiply the speed by 1.8, but the energy goes up by about 9 times. This is the tyranny of the rocket equation combined with relativistic effects. And it gets worse because these calculations assume 100% efficiency in converting your fuel to kinetic energy. In reality, no engine is 100% efficient. Chemical rockets are about 3 to 4% efficient. Ion drives are better, maybe 50 to 70% efficient. Nuclear fusion, if we could build it, might be 70 to 80% efficient. Matter-antimatter annihilation could theoretically be 90% efficient if you could capture all the energy. But even with perfect efficiency, the energy requirements are staggering. A spacecraft weighing 1,000 kilograms, about the mass of a small car, would need about 3 times 10 to the 19th joules to reach 50% the speed of light. That's about the energy output of a large nuclear power plant running for an entire year. All of that energy would need to be stored on the spacecraft or generated somehow during the journey. If you're using fusion, you'd need to carry fusion fuel. Hydrogen is the lightest fuel, but you'd need tons of it. And remember, the more fuel you carry, the more mass you have, which means you need even more fuel to accelerate that additional mass. The rocket equation is brutal. Every kilogram of payload requires multiple kilograms of fuel. Every kilogram of fuel is additional mass that also needs to be accelerated. This is why conventional rockets can't get us to high fractions of the speed of light. The fuel requirements grow exponentially. By the time you've added in enough fuel to reach high speeds, your spacecraft is mostly fuel tanks and you've reached a point of diminishing returns. This is why ideas like laser sails are attractive. If you don't have to carry your fuel, if the energy comes from an external source like a laser beam from Earth, then you avoid the rocket equation problem. But laser sails have their own issues. The laser needs to be incredibly powerful and precisely aimed. The sail needs to be enormous and incredibly lightweight. And once you've accelerated, you can't slow down unless you have a second laser at your destination, which you don't. So laser sails are great for flyby missions where you're just passing through a star system taking pictures, but not for missions where you want to stop and explore. What about more exotic propulsion concepts? There's an idea called the Bussard ramjet proposed by physicist Robert Bussard in 1960. The concept is elegant. As you travel through space, you collect hydrogen atoms from the interstellar medium using a huge magnetic scoop. You then funnel these atoms into a fusion reactor and use the energy to propel the spacecraft. Essentially, you're refueling as you go, scooping up fuel from space itself. This solves the fuel problem. You don't need to carry fuel because you're collecting it along the way. In theory, a Bussarded ramjet could continuously accelerate, eventually reaching speeds close to the speed of light. The problem is that the interstellar medium is incredibly sparse. There's only about 1 hydrogen atom per cubic centimeter in the space between stars. To collect enough hydrogen to fuel a fusion reactor, your magnetic scoop would need to be enormous. Calculations suggest it would need to be thousands of miles across. Building such a structure is beyond anything we can imagine with current technology. And there's another problem. At high speeds, the hydrogen atoms you're scooping up would be hitting you from the front at relativistic speeds. Each atom would act like a tiny particle of radiation. Collectively, they'd create a huge drag force, slowing you down. Some calculations suggest that the drag might actually be greater than the thrust you get from the fusion reactor. If that's true, the Bussard ramjet wouldn't work at all. It would slow you down instead of speeding you up. So the Bussard ramjet is another beautiful idea that probably doesn't work in practice. What about warp drives? This is where we get into really speculative territory. In 1994, physicist Miguel Alcubierre proposed a theoretical way to achieve faster-than-light travel without actually violating relativity. The idea is based on the fact that while nothing can move through space faster than light, space itself can expand or contract at any speed. After all, during the first moments after the Big Bang, space expanded much faster than light. This is called cosmic inflation, and it's a well-established part of cosmology. So Alcubierre proposed that you could create a bubble of space-time around your spacecraft. Behind the ship, space would expand, pushing you forward. In front of the ship, space would contract, pulling you forward. The ship itself wouldn't be moving through space. It would be stationary inside the bubble while the bubble moved through space. Since the ship isn't moving relative to the space immediately around it, it wouldn't violate relativity. But the bubble could move faster than light because space can expand and contract faster than light. It's brilliant, it's elegant, and it probably doesn't work. The first problem is that creating this bubble would require exotic matter with negative mass and negative energy density. We've never observed anything with negative mass. Some quantum effects produce tiny amounts of negative energy density, like the Casimir effect, but nowhere near enough to create a warp bubble. We have no idea how to create exotic matter in the quantities needed. The second problem is that the energy requirements are absurd. Early calculations suggested you'd need the mass-energy equivalent of the entire observable universe to create a warp bubble big enough for a small spacecraft. Later refinements brought that down to the mass energy of Jupiter, which is still impossible, but at least not as ridiculous. More recent work has brought it down further, but we're still talking about energy levels far beyond anything we can generate. The third problem is that you'd have no way to steer the bubble once you're inside it. The front of the bubble is moving faster than light, so you can't send signals to it from inside the bubble. You'd have to set your course before activating the warp drive and hope you've aimed correctly. The fourth problem is that as you travel, you'd accumulate particles and radiation on the front of your warp bubble. When you deactivate the bubble, all that accumulated energy would be released in a massive burst that would likely destroy your destination. So warp drives remain firmly in the realm of science fiction. They are not impossible according to our current understanding of physics, but they require technology and energy sources that might as well be magic. What about wormholes? In general relativity, it's theoretically possible for space-time to be connected in strange ways. You could have a shortcut through space-time, a wormhole that connects two distant points. Travel through the wormhole and you could cross vast distances instantaneously or nearly so. Einstein and Nathan Rosen first proposed this in 1935. Einstein-Rosen bridges, as they're sometimes called, are solutions to Einstein's field equations. They are mathematically valid, but there are problems. First, naturally occurring wormholes, if they exist, would be microscopic, far too small for anything macroscopic like a spacecraft to pass through. To create a traversable wormhole, a wormhole large enough and stable enough to send something through, you'd need exotic matter. Again, specifically, you'd need matter with negative energy density to hold the wormhole open. Without it, the wormhole would collapse the instant you tried to use it. Second, even if you could create a wormhole, you'd have to get one end of it to your destination. If you want a wormhole from Earth to Proxima Centauri, you'd have to transport one end of the wormhole to Proxima Centauri, which means you'd have to make the journey conventionally first, moving one end of the wormhole at less than the speed of light. Once it's there, you'd have a shortcut, but creating the shortcut would take just as long as conventional travel. So wormholes don't really help with the initial exploration of space. They might be useful for maintaining connections between already established colonies, but they don't solve the problem of getting there in the first place. Let's come back to more realistic ideas. What if we embraced the slowness? What if we accepted that interstellar travel will take thousands or millions of years and designed our missions accordingly? This brings us to the concept of generation ships. A generation ship is a spacecraft designed to support multiple generations of humans over centuries or millennia. The idea is that the original crew who leave Earth won't live to see the destination. Neither will their children or their grandchildren. Multiple generations will be born, live their entire lives, and die on the ship. Eventually, after many generations, their descendants will arrive at the destination. This concept raises all sorts of questions. How do you maintain a closed ecosystem for thousands of years? Plants produce oxygen and food, but they need water, nutrients, and light. You'd need to recycle everything perfectly. Every drop of water, every nutrient, every atom of carbon would need to be recovered and reused. We've done this on a small scale on the International Space Station, but never for long periods with complete recycling. Losses are inevitable. Some atoms will get incorporated into structures and not be recoverable. Some will leak out through airlocks. Over centuries, these small losses add up. You'd need massive redundancy and reserves to compensate. How do you maintain genetic diversity in a small population? A generation ship might have a crew of hundreds or thousands. That's a small gene pool. Over multiple generations, you'd see inbreeding, genetic drift, and the accumulation of harmful mutations. This is a serious problem for small populations. We see it in endangered species. When a population drops below a certain size, genetic problems start to appear. You'd need to carefully manage reproduction, possibly using stored genetic material or even genetic engineering to maintain diversity. How do you maintain social cohesion? Everyone on the ship is traveling to a destination they'll never see. They're living their entire lives in a confined space for the benefit of future generations. What keeps them motivated? What prevents social breakdown, conflict, or even mutiny? You'd need strong cultural traditions, a sense of purpose, maybe even religious or philosophical frameworks to give meaning to the journey. And you'd need to preserve knowledge and skills across generations. The people who arrive at the destination need to know how to build a colony, how to survive on a new world. They can't just be passengers, they need to be engineers, scientists, farmers, builders. How do you prevent technological failure? Machines break down, components wear out. Over centuries, every system on the ship will fail multiple times. You'd need spare parts, manufacturing facilities, repair expertise. You'd need to train each generation in the skills needed to maintain the ship. If a critical system fails and there's no one who knows how to fix it, the mission is over. All of these challenges are solvable in principle, but they're difficult, and we've never tested any of this. We've never had a closed ecosystem that's been completely self-sufficient for more than a few years. We've never had a small population isolated for multiple generations. We don't know if it would work. We don't know what problems would arise that we haven't thought of, but let's assume we solve all these problems. Let's assume we build a generation ship that works. How long would it take to travel 1 light year on a generation ship? Well, that depends on how fast the ship travels. If we use nuclear pulse propulsion or fusion drives, maybe we could reach 5 to 10% the speed of light. At 5% travelling 1 light year takes 20 years. That's less than 1 generation. So it's not really a generation ship at that point. At 1% the speed of light, which is more realistic with nuclear electric propulsion, travelling 1 light year takes 100 years. That's 3 to 4 generations depending on how you count. The great-grandchildren of the original crew would be the ones to arrive at 0.1%. The speed of light, which is achievable with advanced ion drives, travelling 1 light year takes 1,000 years. That's about 30 to 40 generations. Nobody alive at the destination would have any living connection to the people who left Earth. The departure would be ancient history passed down through stories and records at 0.01% the speed of light. Travelling 1 light year takes 10,000 years. That's about 300 to 400 generations. Entire civilizations have risen and fallen on Earth in 10,000 years. The crew arriving at the destination would be so far removed from the crew that left Earth that they might not even remember why they're on the ship. The mission could become a mythology, a story about the beginning of time when their ancestors left a place called Earth. This actually raises a philosophical question. If a generation ship travels for 10,000 years, is it still the same mission? The people who arrive have no direct connection to the people who left. They've lived their entire civilization on the ship. In what sense are they still carrying out the mission planned by people who lived 300 generations ago? Do they even want to colonize a planet? Maybe they've adapted to life on the ship. Maybe they've built a functioning society in space and have no desire to leave. Maybe the idea of living on a planetary surface seems strange and unnatural to them. This is one of the strange implications of very long generation ship journeys. The mission could evolve or even be abandoned by people who have different values and desires than the original planners. Now let's think about time dilation again. One of the strange effects of special relativity is that time passes differently for objects moving at different speeds. If you're travelling at a significant fraction of the speed of light, time passes more slowly for you than for people who are stationary. This is time dilation, and it's been confirmed experimentally many times. We've sent atomic clocks on fast-moving airplanes and measured that they tick slightly slower than identical clocks on the ground. GPS satellites have to account for time dilation because they're moving fast relative to Earth's surface. At everyday speeds, the effect is tiny, but at speeds close to the speed of light, time dilation becomes significant. At 50% the speed of light, time passes about 87% as fast. It's decent for the traveller compared to someone stationary. A 10-year journey from Earth's perspective would feel like 8.7 years to the traveller. At 90% the speed of light, time passes about 44% as fast. A 10-year journey would feel like 4.4 years. At 99% the speed of light, time passes about 14% as fast. A 10-year journey would feel like 1.4 years at 99. 9%, time passes about 4.5% as fast. A 10-year journey would feel like 5.4 months. So if you could somehow travel at 99.9% the speed of light, a journey of 1 light year would take about 1 year from Earth's perspective, but only about 16 days from your perspective. You'd aged 16 days, while everyone on Earth aged a year. If you travelled to Proxima Centauri and back, a journey of 8.5 years from Earth's perspective, you'd only age about 136 days, less than 5 months, but everyone you knew on Earth would be 8.5 years older. If you went to a star at 100 light years away and came back, 200 years would pass on Earth, but you might only age a few years. You'd return to an Earth where everyone you knew was long dead, where the world had changed beyond recognition. This is the twin paradox, one of the famous thought experiments in special relativity. If you have identical twins and one stays on Earth, while the other travels at near light speed to a distant star and back, the travelling twin will be younger when they reunite. It's not just an illusion. Time really does pass more slowly for the travelling twin. They really do age less, so time dilation offers a way for individual travellers to make long journeys without personally experiencing the full duration. But it doesn't help with the energy problem. You still need enormous energy to accelerate to 99% the speed of light, and it doesn't help the people left behind. While you're zipping across the galaxy, aging a few years, centuries are passing on Earth. If you ever wanted to return home, you'd be returning to a world that had moved on without you. Everyone you knew would be dead. Your entire society might have changed or collapsed. You'd be a time traveler into the future, unable to go back. This has profound implications for any realistic interstellar travel. Even if we develop the technology to travel at high fractions of the speed of light, even if time dilation makes the journey short from the traveler's perspective, the journey is still impossibly long from the perspective of human civilization. Send a ship to a star 100 light years away, and 100 years will pass before anyone on Earth even knows if it arrived. Another 100 red years would pass before any information came back. That's 200 years total, 8 to 10 generations. Nobody alive when the ship returns will remember the people who left. This makes it very difficult to maintain continuity across interstellar distances. You can't have a unified human civilization spanning many star systems if it takes centuries for information to travel between them. Each colony would be effectively independent, isolated by the vast distances and the finite speed of light. Over time, colonies would diverge. They develop their own cultures, their own languages, maybe even their own subspecies as they adapted to different environments. A colony on a high-gravity planet might evolve to be shorter and more robust. A colony in low gravity might become taller and more fragile. Given enough time, thousands or millions of years, colonies might diverge so much they wouldn't even be the same species anymore. This is speculative, of course. We don't know how fast human evolution would proceed in different environments, especially if we're using genetic engineering or other technologies. But the point is that interstellar colonization, even if successful, wouldn't create a unified human empire like in science fiction. It would create isolated pockets of humanity, each developing independently, connected only by faint signals taking decades or centuries to travel between stars. Now, let's think about the practical economics of interstellar travel. Even if we could build a ship capable of traveling to another star, who would pay for it? The cost would be astronomical. Building a fusion-powered generation ship capable of carrying thousands of people would cost trillions of dollars, maybe tens or hundreds of trillions. It would require decades of construction, massive industrial infrastructure in space, and the dedication of significant resources. What's the return on investment? If you send a colony ship to another star system, and it takes thousands of years to get there, you won't see any benefit in your lifetime. Neither will your children or grandchildren. The colony might eventually send back information, but it will take hundreds or thousands of years to receive it. There's no trade possible across interstellar distances. You can't ship goods between stars because the journey takes too long. By the time your cargo arrives, it's obsolete. Information can be transmitted at the speed of light, which is faster than any ship. But even that takes years or decades. A conversation with a colony 100 light years away would take 200 years for a single exchange of messages. You send a message, 100 years later they receive it. They send a reply. 100 years later you receive their reply. That's not a conversation. That's leaving messages for the distant future. So, there's no obvious economic reason to colonize other stars. No resources you can bring back, no trade you can establish, no strategic advantage. The only reasons are exploration, scientific curiosity, and the long-term survival of humanity. These are noble goals, but they don't generate profit. They don't have immediate benefits. In our current economic system, it's hard to justify spending trillions of dollars on a project that won't produce results for thousands of years. Governments might fund such projects for prestige or long-term planning. But even government budgets face political pressure to show results within election cycles. This is one reason why we haven't seen more progress toward interstellar travel. It's not just that it's technically difficult. It's that it's economically irrational from a short-term perspective. The benefits are so far in the future that they might as well not exist from the perspective of current decision-makers. Of course, this could change if humanity develops a longer-term perspective. If we start planning on timescales of centuries rather than years, we might decide that interstellar colonization is worth the cost. If we become a truly spacefaring civilization with massive infrastructure in the solar system, the cost of building interstellar ships might become more manageable. If we developed self-replicating machines that can build infrastructure autonomously, the cost of space missions drops dramatically. Send a small probe to an asteroid, have it mine the asteroid, and build copies of itself, and soon you have an exponentially growing fleet of machines building whatever you need. With that kind of capability, building a generation ship becomes much more feasible. But we're not there yet. We're still struggling to establish a permanent presence on the Moon. We're still decades away from a human mission to Mars. Interstellar travel is not even on the planning horizon for any space agency. It's something we think about, something we study, but not something we're actively preparing to do, and that's probably wise. There are so many challenges to solve just within our own solar system. We need to learn how to live in space for extended periods. We need to figure out closed-loop life support systems. We need to develop better propulsion systems. We need to build infrastructure for mining and manufacturing in space. All of this is necessary before we can even think about sending humans to other stars. So when you ask how long it would take to travel 1 light year, the technical answer depends on the technology. With current technology over 1,000 years with near-future technology, maybe decades to centuries with far-future technology, maybe years. But the real answer is that we're not travelling 1 light year anytime soon. Not because we can't in principle, but because we haven't solved all the prerequisite problems. We haven't built the infrastructure, we haven't developed the technology, we haven't committed the resources, and maybe we never will. Maybe interstellar travel will remain forever beyond our reach. Not because it's physically impossible, but because it's impractical. Maybe humanity's future is in this solar system, building habitats, terraforming moons, creating a civilization that spans the planets but never leaves the sun's gravitational embrace. There's nothing wrong with that. The solar system is vast, there's room for trillions of people. If we build habitats in space, there are resources enough to support a civilization for millions of years. We could have a rich, diverse, thriving civilization without ever leaving the solar system. Or maybe thousands of years from now, we'll look back at this era and laugh at how limited our thinking was. Maybe we'll have technologies we can't even imagine today. Maybe we'll have solved the energy problem, the propulsion problem, the life support problem. Maybe we'll have colonies around hundreds of stars. Maybe humanity will spread across the galaxy over millions of years, slowly but steadily, expanding our reach. But that's speculation. That's hope for a distant future. For now, for us, 1 light year remains an impossible distance. Let me give you one more way to think about this. Imagine you could convert matter directly into energy with 100% efficiency. This is what happens in matter-antimatter. Annihilation. Every kilogram of matter contains a tremendous amount of energy according to Einstein's equation E equals mc squared. 1 kilogram of matter fully converted to energy produces about 9 times 10 to the 16th joules. That's about the energy in 21.5 megatons of TNT. It's about the energy released by the largest nuclear weapons ever tested. Now let's say you want to accelerate a spacecraft to 50% the speed of light and then decelerate it when you reach your destination. You need energy to speed up and energy to slow down. For a spacecraft with a payload of 1,000 kilograms, you'd need about 2.6 times 10 to the 19th joules. Using matter-antimatter annihilation with 100% efficiency, you'd need about 290 kilograms of fuel, 145 kilograms of matter, and 145 kilograms of antimatter. That's not actually that much. A few hundred kilograms is manageable. But remember, we can't produce antimatter in any meaningful quantity. The total amount of antimatter ever produced by humans is less than 20 nanogs. That's 20 billionths of a gram. To produce 145 kilograms of antimatter at the current rate would take about 300 trillion years. That's about 22,000 times the age of the universe. So even with perfect energy conversion, we're limited by our inability to produce or store antimatter. And this assumes 100% efficiency in converting energy to thrust, which is impossible. Real engines have losses, heat, radiation, inefficiencies in the energy conversion process. You'd probably need several times more fuel to account for these losses. The point is that even in the most optimistic scenarios with technologies that are theoretically possible but practically impossible, traveling 1 light year is still enormously difficult. It requires energy levels and technologies far beyond what we have today, and 1 light year is just the beginning. The nearest star is 4 1/4 light years away. Most stars are dozens, hundreds, or thousands of light years away. The Milky Way galaxy is 100,000 light years across. The nearest large galaxy, Andromeda, is 2 million light years away. The observable universe is 93 billion light years across. 1 light year is tiny on cosmic scales. It's the smallest unit of interstellar distance. And yet it's vast beyond our ability to cross with any technology we can currently imagine building. This is the fundamental reality of living in this universe. The speed of light is finite, distances are vast, energy is limited. We are slow and small and bound to this corner of space by physics itself. You can rail against it, You can dream of warp drives and wormholes and ways to cheat the laws of physics. But until someone discovers new physics, until someone finds a loophole in relativity that we haven't seen in over 100 years of testing, we're stuck with these limitations. The stars are beautiful. They're fascinating. They're full of wonders we'd love to explore, but they're far away. So far away that one light year, the smallest step toward them, might as well be infinite. And yet knowing this, understanding our limitations, there's still something wonderful about looking up at the night sky. Because even though we can't reach the stars, we can see them, we can study them, we can learn about them, we can understand how they work, what they're made of, how they live and die. We can discover planets around other stars. We can search for signs of life. We can wonder if somewhere out there, around some distant star, someone else is looking up at their night sky and wondering the same things we are. The distance might separate us forever, but the question is the curiosity, the wonder. Those are universal. And maybe that's enough. Maybe the journey isn't about physically reaching other stars. Maybe it's about expanding our understanding, pushing the boundaries of knowledge, learning everything we can about this vast universe we find ourselves in. We might never leave this solar system, but our knowledge, our understanding, our curiosity can reach across light years. Our telescopes can see galaxies billions of light years away. Our mathematics can describe the birth of the universe and the death of stars. Our minds can grasp concepts that span time and space in ways our bodies never will. And in that sense, we've already travelled farther than any spacecraft ever could. We've already crossed distances that would take like billions of years to traverse. We've already explored the universe in the only way that really matters, through understanding. So when someone asks how long it would take to travel one light year, the answer is complex. Physically, with current technology, over 1,000 years. With future technology, maybe decades or centuries. With impossible technology, maybe years or months. But intellectually, we've already made that journey. We've already crossed that distance in our minds, in our mathematics, in our understanding of the cosmos. And that journey, the journey of discovery and understanding, never ends. There's always more to learn, always more to discover, always more questions to ask. The physical journey to the stars might be impossible, but the intellectual journey has no limits, and in the end maybe that's the journey that matters most. Let's talk about some specific historical attempts to think about interstellar travel, because humans have been dreaming about reaching the stars for longer than you might think. In 1973, the British Interplanetary Society started a project called Project Daedalus. The goal was to design an unmanned interstellar probe that could reach Barnard's star, a star about 6 light years away within a human lifetime. The design they came up with was ambitious. The spacecraft would use a 2-stage nuclear fusion rocket. The first stage would burn for about 2.05 years, accelerating the spacecraft to about 7.1% the speed of light. Then it would be jettisoned. The second stage would burn for about 1.76 years more, bringing the final velocity to about 12% the speed of light. At that speed, the journey to Barnard's star would take about 50 years. Add a few years for acceleration and you're looking at about 54 years total. The people who launched it might still be alive when it arrives, though they'd be old. The Daedalus design was enormous. The spacecraft would weigh about 54,000 tons at launch. Most of that would be fuel, 50,000 tons of deuterium and helium, 3 to power the fusion reactors. The payload, the actual scientific instruments, would be only about 500 tons, less than 1% of the total mass. This illustrates the tyranny of the rocket equation. To carry 500 tons of instruments, you need 50,000 tons of fuel, a ratio of 100 to 1, and that's with nuclear fusion. One of the most efficient propulsion methods we can imagine. Project Daedalus was never built. It was a design study, an exploration of what might be possible. But it was serious. The British Interplanetary Society spent years working on it. They calculated trajectories, designed engines, figured out how to manufacture helium-3, which doesn't exist naturally on Earth in any significant quantity. You'd have to mine it from the atmospheres of gas giant planets or the surface of the Moon. The conclusion was that Project Daedalus was theoretically possible. Nothing in the design violated known physics, but it would require an enormous commitment of resources and decades of technological development. We'd need to master fusion propulsion. We'd need infrastructure in the outer solar system to mine helium-3. We'd need the ability to build massive structures in space. None of this exists today, and we're not close to having it. In the 80s and 90s, there was a Project Longshot. This was another design study for an interstellar probe. Longshot was designed to reach Alpha Centauri, the nearest star system about 4.37 light-years away. It would use a fusion rocket burning deuterium and helium-3 similar to Daedalus. But Longshot was smaller and slower. It would reach about 4.5% the speed of light and make the journey in about 100 years. Again, the design was feasible in principle, but far beyond our current capabilities. In the 21st century, there have been new proposals. Project Icarus, started in 2009, was a redesign of Project Daedalus using modern technology and knowledge. The goal was the same: design an unmanned interstellar probe that could reach a nearby star within a century. Icarus incorporated improvements in materials, propulsion concepts, and scientific instruments that weren't available in the 1970s. The result was a similar design, but more efficient. Still massive, still requiring fusion propulsion, still far beyond what we can actually build. Then there's Breakthrough Starshot, which I mentioned earlier. This is different from the others because it's actually being worked on now with real funding and real research. Breakthrough Starshot, announced in 2016, is funded by the billionaire Yuri Milner and supported by physicist Stephen Hawking before his death. The idea is to send thousands of tiny spacecraft, each weighing about 1 gram, to Alpha Centauri. These spacecraft would have light sails a few meters across. A powerful ground-based laser array would shine on the sails, accelerating the spacecraft to about 20% the speed of light in a matter of minutes. The journey to Alpha Centauri would take about 20 years. Add another 4 years for the data to come back at light speed, and you're looking at about 24 years from launch to receiving data. This is exciting because it's actually achievable with technology that's close to what we have now. The challenges are significant but not insurmountable. The lasers need to be powerful, but we're building increasingly powerful lasers for other purposes. The sails need to be lightweight and reflective, but we're developing advanced materials. The spacecraft need to be miniaturized, but we're getting better at building tiny electronics. The biggest challenge might be aiming. When you're accelerating a tiny spacecraft to 20% the speed of light using a laser beam, you need to keep that beam focused on the sail for the entire acceleration period. The spacecraft is moving faster and faster, and the beam needs to track it precisely. Even a tiny error in aim would cause the spacecraft to veer off course or the beam to miss the sail entirely. But these are engineering challenges, not fundamental physics problems. People are working on solutions. If Breakthrough Starshot succeeds, it would be humanity's first interstellar mission. A tiny probe weighing 1 gram would cross 4.37 light-years in 20 years. It would send back pictures of the Alpha Centauri system, close-up images of any planets there, data about the system's composition and properties, and all of this would happen within the lifetime of the people who launched it. That's genuinely exciting. It's a real step toward interstellar exploration, even if it's a small one. But notice what Breakthrough Starshot can't do. It can't send humans, it can't slow down at its destination, it can't carry significant scientific instruments. It's a flyby mission, racing past at 20% the speed of light, snapping pictures for a few minutes, then continuing into the darkness. It's better than nothing, but it's not the kind of exploration science fiction has taught us to imagine. We're not sending astronauts to land on an exoplanet and study it up close. We're sending a camera the size of a microchip flying past at 60 million miles per hour, hoping to get a few good images before it's gone forever. This is the reality of interstellar exploration with anything close to current technology. Small probes on fast flyby missions. No humans, no sample return, no long-term study, just a quick glimpse as we race past at a fraction of light speed. And even this requires decades of development and billions of dollars in funding. Now let's think about the human element more deeply. Suppose we did build a generation ship. Suppose we solved all the technical problems and sent a crew of 1,000 people to a star 10 light-years away. At 1% the speed of light, the journey would take 1,000 years. That's about 30 generations. What would life be like on that ship? For the first generation, the ones who volunteered for the mission, there would be excitement. They're pioneers, explorers, part of humanity's greatest adventure. They're leaving Earth behind to ensure humanity's future among the stars. There's purpose and a meaning in that, but they know they'll never see the destination. They'll spend their entire lives on the ship working to keep it running, raising children who will continue the mission. The second generation born on the ship never chose this. They were born into the mission. Earth is a story their parents tell them, a place they've mowed to. They've never seen and never will. The ship is their entire world. By the third or fourth generation, Earth is ancient history. It's a mythical place, the cradle of humanity, but not home. Home is the ship. By the 10th generation, Earth might seem as distant and unreal as Atlantis does to us. A story, possibly true, possibly embellished over the centuries. By the 20th generation, the mission itself might have changed. The descendants might not care about reaching the destination. They've built a life on the ship. They have a functioning society, culture, history. Why give that up to land on some unknown planet? By the 30th generation, when the ship finally arrives, who knows what the people on board will decide to do? Maybe they'll be excited to finally fulfill the mission their ancestors started. Maybe they'll be indifferent or even resentful. Maybe they'll have forgotten why they're traveling in the first place. This is one of the big unknowns about generation ships. We don't know how human societies would evolve in that kind of isolation over that much time. We don't know if the mission would maintain its purpose across generations. There's also the question of knowledge preservation. The people who arrive need to know how to colonize a planet. They need to know agriculture, engineering, biology, physics, medicine. They need practical skills and theoretical knowledge. How do you ensure that knowledge is passed down accurately over 30 generations? One mistake, one generation that doesn't learn something important, and that knowledge could be lost forever? You would need extensive libraries, educational systems, maybe even AI tutors to ensure knowledge continuity. But even then, there's no guarantee. Societies change, priorities shift. What seems important to one generation might be ignored by the next. And if critical knowledge is lost, the mission could fail even after successfully reaching the destination. Imagine arriving at a new world after a 1,000-year journey, only to realize that nobody remembers how to build the equipment needed to establish a colony. The knowledge was in the ship's databases, but nobody bothered to learn it, because they'd lived their entire lives in space and saw no need for planetary survival skills. This is not a far-fetched scenario. The great we've seen knowledge lost on Earth over much shorter timescales. The Romans knew how to make concrete that could last millennia, a technique we only rediscovered in modern times. The ancient Greeks built intricate mechanical computers like the anti-Aether mechanism, knowledge that was lost for centuries. If knowledge can be lost on a planet with millions of people and extensive records, how much more vulnerable is it on a ship with 1,000 people? These are the kinds of problems that make generation ships so challenging. It's not just about building the ship and keeping it running. It's about maintaining a stable, functioning knowledge, preserving society across timescales longer than most civilizations on Earth have lasted. Let's shift perspective again and think about this from the standpoint of physics and the nature of the universe. Why is the speed of light what it is? Why is it 186,000 meters per second and not faster or slower? The speed of light is built into the structure of space-time itself. It's not just the speed that light happens to travel. It's the maximum speed at which any information can propagate through space. It's the speed of causality itself. In special relativity, the speed of light is the conversion factor between space and time. It's what makes space-time a unified four-dimensional structure rather than separate three-dimensional space and one-dimensional time. The fact that the speed of light is finite and has the value it has is fundamental to how the universe works. If the speed of light were infinite, the universe would be very different. Cause and effect would be simultaneous across any distance. There would be no light at travel time, no delay between events. If the speed of light was slower, say 1,000 meters per second instead of 186,000, interstellar travel would be even more impossible. Light would take tens of thousands of years to cross a light year. If we still called it that, if the speed of light were faster, say 1,000,000 miles per second, the universe would be smaller in a sense. Light would cross distances more quickly. Time dilation effects would occur at higher speeds, but the fundamental barrier would still exist. You still couldn't exceed the speed of light, whatever it happened to be. The point is that we're stuck with the universe we have. The speed of light is what it is because of the fundamental constants of physics, the strength of electromagnetic forces, the permeability of free space, the permittivity of free space. These constants determine the speed of light. Change those constants and you'd change the universe in fundamental ways. You might not even have atoms or stars or planets, so we can't wish for a faster speed of light. We have to work within the constraints of the universe we inhabit. And in this universe, 1 light year is a vast distance that takes light 1 year to cross. For anything moving slower than light, which is everything with mass, it takes longer, much longer. If you're using technology anywhere close to what we have now, there's something philosophically profound about this. The universe has built-in limitations. There are places we can see but can never reach even in principle. There are events happening right now in distant galaxies that we won't see for millions or billions of years. By the time the light from those events reaches us, the events themselves are ancient history. The stars we see in the night sky, we're seeing them as they were years or centuries or millennia ago, not as they are now. Betelgeuse, which I mentioned earlier, is about 550 light-years away. The light we see from Betelgeuse tonight left that star in the year 1474. If Betelgeuse exploded as a supernova last week, we won't know about it for another 550 years. The information travels at the speed of light, and the speed of light is finite. This means the universe has a kind of cosmic horizon, not just in space but in time. There are events happening beyond our cosmic horizon that we will never know about because the light from them will never reach us. The universe is expanding and the expansion is accelerating. Distant galaxies are moving away from us faster than the speed of light because space itself is expanding between us and them. Light from those galaxies will never reach us. We can never know what happens there. We can never travel there. Those parts of the universe are fundamentally inaccessible to us now and forever. This is the cosmic horizon and it's shrinking. As the universe continues to expand and accelerate, more and more galaxies will cross beyond the horizon. Billions of years from now, observers in our galaxy will only be able to see our local group of galaxies. Everything else will have receded beyond the cosmic horizon. The universe will appear smaller, lonelier. Unless they have historical records from our era, future astronomers might not even know that there are billions of other galaxies out there. They'll think the universe is just the local group, a few dozen galaxies in an otherwise empty void. This is humbling. We live in a special time when the universe is still young enough and the expansion hasn't progressed so far that we can still see billions of galaxies. We can still study the cosmic microwave background, the afterglow of the Big Bang. We can still observe the large-scale structure of the universe. Future civilizations, if they exist, won't have that privilege. So in a sense, we should appreciate the view we have now. We can see farther and know more about the universe than any future civilization will be able to. Even if we can never travel to those distant galaxies, we can at least observe them, study them, learn from them. That's something. Now, let's come back to the question of why we care about traveling 1 light-year or any interstellar distance. Why does it matter? What's the motivation for wanting to reach other stars? One reason is survival. Earth won't last forever. In about 1 billion years, the sun will have brightened enough that Earth's oceans will evaporate. The planet will become uninhabitable for complex life. In about 5 billion years, the sun will expand into a red giant, possibly engulfing Earth entirely. Even if Earth survives, it will be scorched and lifeless. If humanity wants to survive beyond those timescales, we need to leave the solar system. We need to find new homes around other stars. But 1 billion years is a long time. All of recorded human history is only about 5,000 years. 1 billion years is 200,000 times longer. There's no urgency. We have plenty of time to develop the technology we need. Another reason is curiosity. We want to know what's out there. Are there planets like Earth around other stars? We know there are planets. We've detected thousands of exoplanets using telescopes. But are any of them habitable? Do any of them have life? The only way to know for sure is to go there and look. Telescopes can tell us a lot, but there are limits to what we can learn from light years away. We can analyze the spectra of an exoplanet's atmosphere and look for biosignatures, chemical indicators that life might be present, but we can't be certain without visiting. There could be microbial life that doesn't produce detectable biosignatures. There could be complex life that we miss because we're looking for the wrong signs. The only way to be absolutely sure is to send a probe, or better yet, send humans. But as we've established, sending anything to another star is incredibly difficult. So we're left with a frustrating situation. We know there are thousands of planets out there. Some of them probably Earth-like, some of them possibly inhabited, but we can't reach them. We can only look from a distance and wonder. It's like being a child standing outside a candy store, seeing all the sweets inside, but the door is locked and you don't have the key. The candy is there. You can see it, but you can't have it. That's humanity's relationship with the stars. We can see them, we can study them, but we can't reach them. At least not with anything close to current technology. Maybe that will change. Maybe in a few centuries we'll have fusion drives or antimatter engines or something we haven't thought of yet. Maybe we'll send generation ships to nearby stars, slowly building a network of human colonies across the galaxy. Maybe we'll discover new physics that allows faster than light travel, though that seems very unlikely. Or maybe we'll never leave the solar system. Maybe the distances are just too great and the resources required are too vast. Maybe we'll build a thriving civilization within the solar system. Billions of people living in space habitats and on terraformed moons, but never venturing to the stars. Both futures are possible, we don't know which one we'll get. What we do know is that right now, today, travelling 1 light year is effectively impossible. It would take over 1,000 years with our fastest spacecraft. It would take decades or centuries with optimistic future technology. It would require energy levels and engineering capabilities far beyond what we currently have. 1 light year is a tiny distance on cosmic scales. It's less than the distance to the nearest star, but it's vast by human standards. It's a distance that might as well be infinite given our current limitations, and that's the reality we have to accept. We live in a universe where distances are immense and speeds are limited. We're slow creatures on a small planet looking out at a cosmos we can observe but not traverse. It's humbling. It's frustrating, but it's also beautiful in its own way. The universe is vast and mysterious. There are wonders beyond counting spread across billions of light years. We'll never see most of them in person, but we can imagine them. We can study them from a distance. We can dream about them. And maybe that's enough. Maybe the journey isn't about reaching the stars physically. Maybe it's about reaching for understanding, pushing the boundaries of knowledge as far as we can, learning everything we can about this incredible universe we find ourselves in. Because even though we can't travel 1 light year in a human lifetime, we've already explored the universe in ways that matter. We've mapped galaxies billions of light years away. We've detected gravitational waves from black holes colliding in the distant past. We've observed the cosmic microwave background, light from when the universe was only 380,000 years old. We've discovered thousands of exoplanets and learned that planets are common throughout the galaxy. We've developed a mathematical description of the universe from its first moments to its ultimate fate. We've done all of this without leaving Earth, or at most without going farther than the moon. Our bodies might be confined to this small corner of space, but our minds, our understanding, our knowledge, they've travelled farther than any spacecraft ever could. And in the end, that might be the most important journey of all. Let me give you some more ways to grasp just how impossibly far 1 light year really is. We've talked about time, how long it takes to travel that distance, but let's talk about it in terms of scale in ways that might make it more concrete. If you could drive a car at highway speed, 60 miles per hour, continuously without stopping, how long would it take to drive 1 light year? 1 light year is 5,878,625,000,000 miles. Divide that by 60 miles per hour. That gives you about 97,977,000,000 hours. Convert to years, that's about 11,181,000 years. Over 11 million years of continuous driving. Modern humans have only existed for about 300,000 years. You'd need to have started driving before modern humans evolved. You'd need to have been driving when our ancestors were still Homo erectus, a different species entirely. When there were no cars, no roads, no wheels, no civilization of any kind. When humans were just beginning to use stone tools and control fire, and you'd still be driving today, and you'd still have millions of years to go, that's 1 light year at 60 miles per hour. What if you could walk? The average walking speed is about 3 miles per hour. At that pace, walking 1 light year would take about 222,362,000 years. That's longer than the time since the dinosaurs went extinct. The asteroid that killed the dinosaurs struck Earth about 66 million years ago. You'd need to walk more than 3 times longer than that. You'd need to have started walking before there were any primates, before there were any mammals larger than a shrew when dinosaurs still ruled the Earth, and you'd still be walking today, and you'd still have over 150 million years left to go. What if you could run? A marathon runner maintains about 6 miles per hour for over 26 miles. That's faster than walking but slower than driving. At 6 miles per hour, running 1 light year would take about 111,181,000 years. That's still longer than the age of the dinosaurs. What if you took the fastest commercial airliner? A Boeing 747 cruises at about 570 miles per hour. At that speed, flying 1 light year would take about 1,176,000 years. We're back to timescales longer than modern humans have existed. Every form of transportation we have, from walking to the fastest jets, is pathetically slow compared to the distances between stars. Even our fastest spacecraft, the Parker Solar Probe, at 430,000 miles per hour, would take 1,560 years. Let's think about this another way. Light can circle Earth's equator about 7 and 12 times in 1 second. In that same second, how far does our fastest spacecraft travel? The Parker Solar Probe travels about 119 miles in 1 second. Light travels about 1,391,200 meters in that same second. Light is about 11,692 times faster than our fastest spacecraft. That's the gap we're trying to bridge. We're not even close. We're not within an order of magnitude. We're not within 2 orders of magnitude. We're off by more than a factor of 10,000. Here's another comparison. The distance from Earth to the Moon is about 238,900 meters. Light takes about 1.3 seconds to travel from Earth to the Moon. Radio signals traveling at light speed take about 1.3 seconds to reach the Moon. That's why there's a noticeable delay in conversations between astronauts on the Moon and mission control on Earth. The Parker Solar Probe would take about 33 minutes to travel from Earth to the Moon. Now compare that to 1 light year. 1 light year is about 24,665 billion times the distance from Earth to the Moon. That's a number so large it's hard to comprehend. If you could fit 24,665 billion Moon-Earth distances end to end, you'd have 1 light year. Here's another way to think about it. The distance from Earth to the Sun is about 93 million miles. We call this distance 1 astronomical unit or 1 astronomical unit. Light takes about 8 minutes and 20 seconds to travel 1 astronomical unit. If the Sun suddenly disappeared, we wouldn't know for 8 minutes and 20 seconds because the information would travel at the speed of light. The Parker Solar Probe would take about 9 days to travel 1 astronomical unit at its maximum speed. 1 light year is about 63,241 astronomical units, 63,241 times the distance from Earth to the Sun. If you made a scale model where Earth and the Sun were 1 inch apart, how far away would you have to place an object to represent 1 light year? 63,241 inches, that's about 5,270 feet. About 1 mile, so on a scale where Earth and Sun are 1 inch apart, 1 light year is about a mile. And the nearest star Proxima Centauri is 4.24 miles away on that scale. The centre of the Milky Way is about 26,000 miles away. The Andromeda Galaxy is 2.5 million miles away. These scales are hard to wrap your mind around. No matter how you slice it, 1 light year is vast. It's a distance that dwarfs anything we experience in everyday life. It's a distance that dwarfs the entire solar system. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. 1 light year is 2,108 times the distance from the Sun to Neptune. If Neptune's orbit was 1 inch in diameter, 1 light year would be 175 feet away. That's the height of a 15-story building. Now, let's think about what it would be like if we could actually travel 1 light year. Suppose you got on a spacecraft that could travel at 50% the speed of light. You would reach your destination in 2 years of ship time, though more time would pass on Earth due to time dilation. What would you see at first? As you accelerated, the stars behind you would shift colour. Light from stars behind you would be red-shifted as you moved away from them. Light from stars ahead of you would be blue-shifted as you moved toward them. This is the relativistic Doppler effect. As you approached 50% light speed, the shifts would become dramatic. Stars ahead would appear bluer and brighter. Stars behind would appear redder and dimmer. The distribution of stars in the sky would appear to change. More stars would appear to be concentrated ahead of you, fewer behind. This is called relativistic beaming or the headlight effect. The faster you go, the more pronounced it becomes. At 90% light speed, almost all the starlight would appear to be coming from a small cone ahead of you. The stars behind and to the sides would appear to dim almost to invisibility. As you travelled, nearby stars would show parallax. Their positions relative to distant background stars would shift as you passed them. At 50% light speed, covering half a light year in 1 year, nearby stars would noticeably change position. Stars that were ahead of you would pass to the side and then behind. Stars that were to the side would shift to behind you. New stars would appear ahead. You'd see the constellations change. Familiar patterns would distort and eventually become unrecognizable. The Big Dipper, Orion, Cassiopeia, all the constellations you've known would shift and morph. New patterns would emerge, and when you arrived 1 light year away from where you started, the night sky would be completely different. Earth's sun would be just another star among thousands. Not particularly bright or remarkable, just one more point of light in the darkness. If you had a powerful enough telescope, you could look back and see the solar system. You could see the planets, tiny dots of reflected light orbiting a yellow star. You could see Earth, a pale blue dot like the famous Voyager photograph, but from a different angle. You might feel the isolation. You'd be farther from home than any human has ever been. Farther than the moon, farther than Mars, farther than any planet. You'd be in interstellar space in the vast darkness between stars. The nearest star to you might be several light years away. You'd be utterly alone, surrounded by emptiness with no hope of rescue if something went wrong. This is the reality of interstellar travel. Even if we could travel at high fractions of light speed, even if the journey only took a few years, it would be a profound psychological challenge. The isolation would be absolute, the distance would be incomprehensible, the risk would be enormous, and yet some people would probably volunteer for it. Throughout history, humans have always been explorers. We've crossed oceans in wooden boats, not knowing what lay on the other side. We've climbed mountains because they were there. We've explored caves, deserts, polar ice caps, the deepest parts of the ocean. We've sent astronauts to the moon, knowing the risks. When given the chance, some humans always choose to explore, to push boundaries, to see what's over the next horizon. If we ever develop the technology to travel to other stars, there will be volunteers, people willing to leave everything behind, knowing they might never return for the chance to see something no human has ever seen. To set foot on a planet orbiting another star, to be the first. That drive, that curiosity, that willingness to risk everything for discovery, that's one of humanity's defining characteristics. It's taken us from small tribes in Africa to a global civilization. It's taken us to the moon and sent our robots to every planet in the solar system. Maybe someday it will take us to the stars. But that day is not today. Today, 1 light year remains an impossible distance. Now, let's talk about what we've accomplished despite these limitations. In the last few decades, we've discovered thousands of exoplanets, planets orbiting stars other than the Sun. Before 1992, we didn't know of a single planet outside our solar system. We suspected they existed, but we had no proof. Then in 1992, astronomers discovered the first confirmed exoplanets orbiting a pulsar. In 1995, they discovered the first planet orbiting a Sun-like star, 51 Pegasi b. Since then, we found thousands more. As of the latest count, we know of over 5,000 confirmed exoplanets, with thousands more candidates waiting to be confirmed. We've found planets of every type imaginable. Hot Jupiters, giant planets orbiting close to their stars, heated to thousands of degrees. Ice giants like Neptune but orbiting other stars. Rocky planets like Earth. Some in their star's habitable zone where liquid water could exist. Super-Earths, rocky planets larger than Earth but smaller than Neptune. Many Neptunes. Planets between Earth and Neptune in size. We found planets orbiting binary stars, something that was thought to be impossible. We found planets orbiting the remnants of dead stars. We found planets that orbit their stars backwards in retrograde orbits. We found planets that are pitch black, absorbing nearly all the light that hits them. We found planets that might rain glass sideways due to their extreme winds. We found planets that might have oceans of liquid lava. We've even found a few planets that might be genuinely Earth-like. Rocky planets about Earth's size, orbiting in the habitable zone of Sun-like stars where temperatures might allow liquid water. Planets like Proxima Centauri b orbiting the nearest star to our Sun. Planets in the TRAPPIST-1 system where 7 Earth-sized planets orbit a small red dwarf star. 3 of them in the habitable zone. Planets around Kepler, 442, Kepler 452 and dozens of other stars. We don't know if any of these planets actually have life. We can't see them clearly enough to know. They're too far away and they're too small and dim compared to their stars, but we're working on it. The James Webb Space Telescope, launched in 2021, is analysing the atmospheres of exoplanets. By looking at how starlight filters through a planet's atmosphere during a transit, when the planet passes in front of its star, we can determine what gases are present. Oxygen, methane, water vapour, carbon dioxide, all of these leave distinct signatures in the spectrum. If we find oxygen and methane together, that might indicate life on Earth. Oxygen and methane don't coexist naturally. Oxygen reacts with methane and destroys it. The only reason we have both in Earth's atmosphere is because living organisms constantly produce both. Plants produce oxygen. Bacteria and cows and other organisms produce methane. Without life continuously replenishing both gases, they'd react and disappear. So if we find a planet with both oxygen and methane in its atmosphere, that's a strong hint that something is producing those gases, that something might be life. We haven't found such a planet yet, but we're looking. And the fact that we're looking, that we're analysing the atmospheres of planets orbiting stars dozens or hundreds of light years away is remarkable. We can't go there. We can't send a probe. We can't travel 1 light year, let alone dozens or hundreds. But we can study those planets from here. We can learn about them. We can search for signs of life. And if we find it, if we discover life on another world, it will be one of the most profound discoveries in human history. Even if we can never go there, even if we can never meet whatever forms of life might exist, just knowing that life exists elsewhere would change everything. It would tell us that we're not alone. It would tell us that life is not a cosmic fluke, a one-time accident that happened only on Earth. It would tell us that the universe is teeming with life, that wherever conditions are right, life finds a way. And maybe someday we'll find intelligent life. Maybe we'll detect radio signals from a distant civilization. Maybe we'll see the signatures of technology, heat signatures from megastructures, or unusual spectral lines from industrial pollution. Maybe we'll find evidence that we're not the only species that has built a civilization that has looked up at the stars and wondered. And if we do, what then? We still can't travel to them. If they are 100 light years away, any message we send will take 100 red years to reach them. Their reply will take another 100 red years to come back. A single exchange of messages would take 200 years. Everyone involved in sending the first message would be dead before the reply arrived. But maybe that's okay. Maybe just knowing they're there is enough. Maybe the conversation itself, spanning centuries, is valuable. Even if no individual experiences both sides of it, humanity could have a dialogue with another civilization, exchanging ideas and information over thousands of years. Our great-great-great-grandchildren would receive messages that we sent. Their great-great-grandchildren would receive our replies. It would be a conversation unlike any other in human history. Slow, patient, spanning generations, but real. This is the kind of future we might actually have. Not Star Trek with ships zipping between stars in days or weeks. Not Star Wars with hyperspace jumps across the galaxy, but a future where we're connected by light, by radio waves, by information travelling at the speed of light between stars. Where we explore the universe not with our bodies, but with our telescopes and our minds. Where we search for life, for intelligence, for understanding across vast distances that we can never physically cross. It's not as exciting as science fiction, but it's so real, and there's a beauty in that. A beauty in accepting the limitations of the universe and finding ways to work within them. A beauty in recognizing that we don't need to travel to the stars to explore them. We just need to look, to listen, to learn. So when someone asks how long it would take to travel 1 light year, the answer is both simple and complex. With our current technology, over 1,000 years. With near-future technology, perhaps decades to centuries. With far-future technology that might never exist, perhaps years. But the deeper answer is that maybe we don't need to travel 1 light year. Maybe we can accomplish everything that matters without leaving home. We can study the universe from here. We can search for life from here. We can expand our knowledge and understanding. From here, we can build a civilization in our solar system. From here, we can ensure humanity's survival by spreading to multiple worlds in our own solar system. We can create art, science, culture, meaning, purpose, all from here. And maybe that's enough. Maybe the stars don't need to be destinations. Maybe they can just be inspirations, points of light in the sky, that remind us how vast the universe is, how small we are, how much there is to learn and discover. 1 light year is an impossible distance, but it's also just a measure, a unit we invented to describe the space between stars. The distance itself hasn't changed. The stars have always been this far away. What's changed is our understanding. We've learned how far they are. We've measured the distance. We've done the math and realized just how long it would take to get there. And in doing so, we've learned something about ourselves. We've learned that we're bound to this corner of space, at least for now. We've learned that the universe is bigger than our ambitions. We've learned humility. But we've also learned something else. We've learned that even with these limitations, we can still accomplish remarkable things. We can still explore. We can still discover. We can still push the boundaries of knowledge. Just because we can't travel 1 light year doesn't mean we can't reach across 1 light year. Our telescopes can see across light years. Our radio dishes can listen across light years. Our minds can comprehend concepts that span light years. We've already crossed that distance in every way that matters except physically. And maybe in the end, that's the real achievement. Not building faster ships, not finding loopholes in physics, but expanding our understanding to encompass distances we can never personally traverse. That's the human story. We're creatures who evolved on one small planet, adapted to think about distances measured in miles and times measured in days. But we've taught ourselves to think about light years and millions of years. We've stretched our minds to encompass the cosmic scale. We've made the infinite comprehensible, and that's worth celebrating. So yes, it would take over 1,000 years to travel 1 light year with current technology. Yes, the stars are unreachable with anything we can build today. Yes, the universe is vast and we are small and slow, but we're also curious and intelligent and persistent. We're also dreamers and explorers and learners. We're also the species that looked up at the night sky and asked, how far away are those stars? And then figured it out. We measured distances so vast they boggle the mind. We calculated travel times that span millions of years. We designed spacecraft that exist only on paper, but could theoretically cross interstellar space. We searched for planets around other stars and found thousands. We're searching for life in the universe, and maybe one day we'll find it. We've done all of this from one small planet using nothing but our minds and the tools we've built. And that's incredible. That's worth more than any physical journey could ever be, because the journey isn't about travelling 1 light year. The journey is about understanding what 1 light year means. The journey is about grasping the scale of the universe. The journey is about looking up at the night sky with knowledge and wonder. The journey is about being here now, in this moment on this planet, looking out at the cosmos and comprehending our place in it. And that journey, that intellectual and spiritual journey, is one we can all take right here, right now, without travelling a single mile. That's the real answer to how long it takes to travel 1 light year. In body, thousands of years. In mind, an instant.